Welcome to Numerical Analysis. Today we are going to explore the Gauss-Seidel method. Imagine trying to guess the exact number of jelly beans in a jar with your friends, where every time someone makes a better guess, you immediately use their information to improve your own. This is a brilliant mathematical shortcut for solving complex systems of equations by making educated guesses that constantly improve themselves. Let us dive in and see how it works. Now that we understand the basic premise, let us look at what this method actually is. The Gauss-Seidel method is an iterative algorithm used to solve a system of linear equations. An iterative algorithm is simply a repeating step-by-step process that gets closer to the truth with each cycle. Instead of trying to solve everything perfectly in one shot, we start with an initial guess for all our unknown variables, usually just zeros. The defining feature here is continuous, immediate updating. As soon as we calculate a new, better value for one variable, we immediately plug it into the next equation. We do not wait for the round to finish. Before we jump into the math, we must know if this method will actually work for our specific problem. The Gauss-Seidel method only works reliably if the system of equations is diagonally dominant. What does this mean? It means that in each equation, the number attached to the main variable we are solving for must be larger than the sum of the other numbers in that same equation. If you ignore the positive or negative signs, the main diagonal number must be the heaviest weight in its row. If it is not the heaviest weight, our guesses might explode into infinity instead of settling on the right answer. With the conditions clear, let us look at how we set up our formulas. We start with the standard general form of a linear equation. To use this method, we must rearrange the equation to isolate our first target variable, x1. We move everything else to the right side of the equal sign and divide by the coefficient a11. This gives us a direct formula to calculate a new guess. In this formula, the letter a represents the known coefficients. X represents the unknown variables and B represents the constant numbers. We do this exact same isolation process for every single equation in our system. Now that we have our isolated formula, we need a way to track our old and new guesses. We introduce iteration counters using superscripts. We use a superscript with the letter K to represent our old, current guess. We use the superscript k plus 1 to represent the brand new guess we are calculating right now. This notation is crucial because it helps us keep track of which numbers are fresh and which are outdated. If the old guesses change, the new guess will shift accordingly, pulling us closer to the true solution with every single cycle. This brings us to the most important formula in the entire method, the second equation. Look very closely at the term for the first variable here. It has the new k plus 1 superscript attached to it. This is the absolute core secret of the Gauss-Seidel method. We use the brand new value we just calculated a fraction of a second ago, rather than the old guess. However, notice that we still have to use the old guess for the third variable, because we have not reached its equation yet. This immediate updating is what makes the method so incredibly fast. Before we move on, let us see this with a concrete example. We are given a system of 3 equations and asked to solve for x, y, and z. We will start with an initial guess of 0 for all variables. First, we must check for diagonal dominance. In the first equation, 4 is greater than 1 plus 1. In the second, 5 is greater than 1 plus 2. In the third, 6 is greater than 1 plus 1. Because the main diagonal numbers are the heaviest weights, the system is diagonally dominant. We can safely proceed by rearranging each equation to isolate our variables. Now that our system is set up, we can begin our first round of calculations. We have isolated the first variable, x, by moving the others to the right side and dividing by 4. We will use this formula to find our first updated value. We plug in our initial guesses of 0 for the old variables, y and z. By substituting these initial zero values into the equation, we simply perform the basic arithmetic inside the parentheses. 6 minus 0 divided by 4 gives us exactly 1.5. We have found our first brand new value. With our first new value in hand, we immediately move to the second equation. Because this is the Gauss-Seidel method, we will immediately throw away our old guess of 0 for x. We will use this new value of 1.5 in the very next step. This is the rearranged formula for our second variable, y. Notice that it asks for the new value of x but still needs the old value of z. We substitute our brand new value of 1.5 and our old guess of 0. Multiplying and subtracting gives us a new y value of 1.3. Having updated two variables, we are now ready to solve for the third. This is the rearranged formula for our third and final variable, z. It is the luckiest equation because it gets to use the fresh, highly accurate numbers for both of the previous variables. We plug in the new values of 1.5 for x and 1.3 for y. We subtract these numbers from 8 to find the final numerator and divide by 6. This gives us 0.8667. We have now completed the first full round of calculations. To see how the numbers settle down, let us perform a second round of calculations. We will use our results from the end of the first round as our starting point. We use the exact same rearranged equations as before. The strategy remains identical. Plug in the most recent numbers available, calculate a new value, and immediately use that new value in the next equation. We start by updating our first variable again. We substitute the y and z values from the end of round 1 into the formula. This gives us a newly updated x value of 0.9583. Just like before, we carry this fresh x value forward immediately. We have our newly updated first variable, so we immediately discard the old value of 1.5. We substitute the brand new value for x while still using the older value for z from the end of round 1. We simplify the arithmetic inside the parenthesis, subtracting from 8 and dividing by 5. This gives us our newly updated second variable, y, which is 1.0617. We now have fresh numbers for the first two variables to use in the final equation. We now bring our two freshest numbers into the final step of this iteration. We substitute both of our brand new values for x and y into the final equation for z. We perform the final subtraction and division by 6. This yields 0.9967. After just 2 rounds, our values are approximately 0.96, 1.06 and 1.00. The true exact answer to this system is actually exactly 1 for all 3 variables. You can see how incredibly fast this method pulls our guesses toward the perfect answer. To truly visualize why this method is so fast, let us look at a flowchart of the process. On the screen, you can see the initial guess block at the top left feeding into the first equation for x. The critical part of this diagram is the thick red arrow pointing straight down. It shows the new x value bypassing the old data and flowing directly into the equation for y. Then, both the new x and new y flow directly into the equation for z. This continuous cascading of fresh data is the heartbeat of the Gauss-Seidel method. Now that we have seen how it works, you might wonder why this matters outside the classroom. In the real world, engineers rarely solve systems of just 3 equations. When designing the power grid for a whole city or simulating how heat flows through a car engine, they have to solve millions of equations at the same time. Direct methods would take a supercomputer weeks to solve and require too much computer memory. The Gauss-Seidel method is a lifesaver because it requires very little memory. It just overwrites the old numbers with the new ones, making it highly efficient. Let us wrap up by reviewing the most important ideas we have covered today. First, the Gauss-Seidel method is an iterative algorithm that solves systems of linear equations by constantly updating guesses. Second, its defining feature is that it uses the most recently calculated values immediately, which drastically speeds up the journey to the correct answer. Finally, it requires the system to be diagonally dominant to work reliably. You have now covered the full topic and understand both the mathematics and the real-world power of this incredible algorithm. Great job!